Alrighty then. Hey guys, what's going on? Memes here. Yes, yes, I know. What a preposterous claim. I'm a preposterous person, I claim. So how we all doing? I see we got Lucy in there. Good to see you, Lucy. Good to see you. We need to catch up as well as we got NS. Ooh, we this is gonna be fun. Well, let's now to be fair, can't get the I can't go from nothing to something. Well, unless you want to do one over nothing, 'cause then you'll get like a complex infinity or something. That aside, within the standard paradigm of our standard Big Bang cosmology, lambda, CDM, basically cosmological constant stuff that's moving us around through the cosmos, seemingly, as well as cold, dark matter. Basically, there's a bunch of mass out there and we can't see it. So basically, it's more like invisible matter. Uh, Personally, I am very biased on this. I think they should rename black holes to mass holes. Now, as a mass hole born and raised, I think that would be needed and a little bit more telling as well. So here's what we're gonna do. Thing is, I've been MAA for a while, and then I just decided let's just clip some of Thad's video and then just give it the totally not preposterous title of "If I Were God, How Would We Make This Universe?" or something along those lines. Let's see. Here we go. What's the actual quote? If I were God, how would I go about creating this universe? Okay, so we're gonna play a little bit of this, and again, that might do we necessarily agree on everything? No, but I think, and again, I am very biased on this. I think that has come across some very interesting things. And I'm just a dude on the internet. I'm not a traditionally trained quantum mechanic, mathematician, or something. I just I like to listen to smart folks and the benefit of the time that we live in. We have access to like the Library of Alexandria plus thousands of years of all the collection of human knowledge, like mostly free. Uh Personally, I think most knowledge should be free. That's the take. So basically, I'm going to take Thad's idea. We're going to let him lay out the basic of it. You can feel free to watch it. Links in the doobly doo. But we're going to watch his initial concept, and then I'm going to try to flush it out. And again, could be totally wrong here, but it seems to adhere to a lot of what's maybe going on. And I'm sure there's flaws, but it's like for me, I'm ultimately a gamer, so I might not know all the different rules of the game, but I start to learn the different framework. And as it gets set up, I notice different properties because whether you have a special move, whether it's a Pokemon card, a Yu Gi Oh card, something like that, you have certain attributes, abilities, things that are effective in particular situations. I also think that's probably one of the reasons why you have a whole bunch of different smart folks coming from different methods and formulations and seeming to be able to explain a lot. I don't think that's a coincidence. Personal opinion. All right, let's see what that had to say.
If I were God, how would I go about creating this universe?
Yeah,
Essentially.
yeah.
Hey,
I want
welcome.
a complete
Kale, I got a video
deterministic
coming up about that.
containment of the actual
We'll get
essence
halfway
of
there.
reality. Right now, I have a list of numbers that means nothing. You could memorize all the numbers and hold them in your head, and still you wouldn't have a picture that contained those properties in its structure in any way. You just memorizing a list.
So that's one of the big when I talk to different folks and they're like, "Oh, I don't know any of that stuff." It's like I give the quick analogy. I'm like, listen, there might be two kids that love playing Fortnite. They might be talking vehemently about it. Have no idea what the heck they're talking about. But if I was into that, you start to learn the different things, and then guess what? You learn how to play Fortnite, and maybe if you're into it, maybe you start to get kind of good or something like that. It's the same thing. You have to be interested in something. You might be able to do something, but if you don't like doing it, oh, personally, I think that stinks. if you happen to be in something, really into something, I kind of view that like kind of like an experience bonus thing where you're probably more likely to be able to pick it up more easily than something you're not interested in. Personal opinion. I think that's worth stressing. Continue. Oh, basically, I always say it's like, yeah, there's a whole bunch of numbers and stuff. Okay, well, yeah, there's a bunch of numbers. Okay, what are the numbers mean? I don't know. It's about the relationships, because once you define a coherent unit system, basically that whole, oh, once you get F plus MA, you can get basically everything. That seems to make a lot of sense. It might be true. I'm sure there's probably more than that. I heard that from Professor Carroll, but that whole force equals mass times acceleration. What's acceleration? You go a unit of length, you divide it by time squared. So it's per second per second. Okay. And then you get to your energy. What is energy? Well, it's force times distance. So what happens? You get your mass, you get your one thing of length, you get two things at a time, you add another length. Oh, wait, mass, length, time. Oh, look, it's C squared. You get your energies. And then power is just that divided by time. Coincidentally, if you can set up that structure, you don't necessarily need to introduce different constant factors. Or at least that's what the Wikipedia article said, claiming from Maxwell's and stuff like that. Again, take it with a grain of salt, but that seems to be a very useful thing. I'm sorry, I'm
I'm
bloating.
not just here to report the effort. I actually have fantastic news of where we got. We actually have found a story that goes all the way from the beginning out. And let me see if I can tell it. If we imagine starting without a universe, okay? Let's say exactly what we mean. There's an infinite void. There's no stuff in it. There's random waves going everywhere. There's nothing that repeats. There's nothing that persists. If you and
Okay. So let's note this. Let's put this into some context of some other things that we, or at least I am pretty sure a lot of folks have started but hearing recently. Professor Barondess out of Harvard, he's been using the term your configuration space. So whether you happen to be particular to an infinite dimension, Hilbert space, I don't know, maybe if you want to use a naturally logarithmic basis of construction. My two postulates are math works and logs are useful, and then we go from there. People may disagree with that. I think it's pretty good, but basically, when you say nothing, he is technically still invoking, oh, there's waves. That's kind of a thing. He's basically saying there's something, a lack of coherence. So this is the point where, okay, we got some maybe quantum fluctuations. There's some fluctuations of a thing. This is also where it gets useful if you want to invoke the Wolfram-Ruliad, because if you're just going to say it's the infinite entanglement of all things, it kind of sounds like an infinity groupoid. So you're putting all the potential things there, and then at some point you're going to get a thing that will probably arise that kind of looks like where we are. I think that's also how we get Boltzmann brains. Brains. I feel like we need more Boltzmann brain zombie memes. Maybe I haven't paying attention recently enough. I'm sorry, Thad, I cut you off. We continue.
I were gods looking at this infinite void, but somehow not in it, because then we would have stuff in that void, right? If that were a thing we could say coherently, and we were looking at it, you could point to anything in there to try to tell me, look at the character here, and then if I looked, I would not find it. Okay? So anything that does happen there never happens again. That's what I mean by infinite void of nothingness. Okay? Nothing is repeatable. Nothing is measurable. Nothing can be made sense of. By definition.
Chaos.
It's chaos and endless. Okay. I want to ask, what does it take to go from that nothingness to something? To have something that persists? Anything, the minimal possible thing. What's the smallest step from this nothing, chaos, infiniteness to a universe of structured order? It turns out mathematicians have already found the answer to this.
Okay.
I was, trained classically through physics, and we were not trained anything, at least not to my training. anything about knot theory, okay? But it turns out that there are a whole class of knots. There's the simplest one all the way to more and more infinite complexity, combining more and more features of the knots, right? But the simplest possible knot is called the hyperbolic figure 8 knot, okay? And it's the simplest possible hyperbolic knot. There's one simpler one that's only 3 instead of 4, called the trefoil knot, but it's not hyperbolic. What's cool about hyperbolic is all hyperbolic knots admit rigid structures. If you formed a hyperbolic knot, then the complement of that knot being formed, the wave motion of everything else in reaction to the formation of the knot, emits a rigid structure, a grid,
A parameter.
a grid that repeats the whole thing over and over and over. Okay, each knot gives you different rigid structure.
Okay. This is worth just for a moment to do a tangent. I've got Casey looking into this more just because what Thad just invoked there, I'm like, I think I've heard him say that, but I'm like, all right, what is that? So let's take a look at what that appears to be. That appears to be, hang on this tab. All right, so go from Wikipedia. Hyperbolic volume. This appears to be by Mostow rigidity. So basically, when a link complement has a hyperbolic structure, this structure is uniquely determined, and any geometric invariants of the structure are also topologically invariants of that link. Basically, in particular, the hyperbolic volume of the complement of a knot, in order to make it defined for all, basically it needs the volume is going to be the same for its different iterations. So what is this? Essentially, basically all these different versions. The Mostow-Prasad rigidity theorem essentially states that the geometry of a complete finite volume hyperbolic manifold of dimension greater than 2 is determined by the fundamental group. And I'm like, oh, what's the fundamental group? In mathematics, the field of algebraic topology, the fundamental group of a topological space is the group of equivalence classes under homotopy of the loops contained in the space. Okay, so it's remaining the base. Okay. So it sounds like you have the ability to create something with the same hyperbolic volume and its different iterations. Okay, why is that interesting at all? Okay. I don't know what all this means. So if full disclosure, I'm going in there, I'm looking at the parameters to see if this makes sense. So basically, it seems like a way of actually covering and going through that. So, hey, Jax. So when does nature just use sound? Yeah. When we say sound, I like the term oscillation. Why? Because an oscillation can be a vibration. It could be kind of like a wavy thing. I think that's a little bit more encompassing. But who doesn't like good vibration? Okay. Okay. So basically, manifold greater than 2. All right. Geese king, hyperbolic figure 8 knot. Okay, those are 3 manifolds. Check. All right. Okay. Yes. Okay, that was a tangent there. Well, the interesting thing is if we go to the figure 8 knot, the fundamental group, and again, I need to up myself on my mathematical knowledge of stuff, is it has the figure 8 knot and the pretzel knot are the only 2 hyperbolic knots known to have more than 6 exceptional Dane surgeries, resulting in a non-hyperbolic 3 manifold. They have 10 and 7 respectively. Basically, the figure 8 holds 10, and this appears to be the maximum number of exceptional surgeries on any hyperbolic knot. I remember I was going through, I got a paper somewhere where it was going through, and you're just looking at the angle of how things are oriented and how things would play out and stuff. So I'm like, all right, if there's 10 there, might that be a potential clue of, I don't know, maybe why our logs are useful? Listen, I don't know. I'm grasping for straws. I think it's an interesting thing. Okay. Now that we've scared folks away with the Moscow rigidity theorem, because that screams excitement for your average Sally Dicker it was a fascinating thing. And I listened to a lecture and oh, oh, it was from Yale from like, I think a few years ago, but I'm like, he was saying all the right words. And I'm like, Casey, check to see it. I don't want to overreact. So I realize I am overreacting here, but let's get back to Thad's explanation. He was just talking about how if you had supposedly a void and you just kind of have like randomness waves, it's just some randomness of things. How could we get to where we are? Let's pick this back up. Continue, Thad.
But each knot emits a rigid structure if it's hyperbolic. Okay. There's the simplest possible manifold.
So yeah, what does hyperbolic mean? What you just said, is that the definition of hyperbolic?
Great question. What does hyperbolic mean? I'm going to try to answer that like 5 ways. Okay. First of all, the classic hyperbolic
we're going to get to the
structure in mathematics is shown like this with this conic center to it. The cone on cone.
You can go watch Thad's original
Right, this is
video. Or I think I put the link to this.
Right there.
Yeah, like a torus almost.
Yeah. And if you multiply it by 2, you get the hyperbolic figure 8 knots volume. The volume complement of the hyperbolic figure 8 knots. Okay. It's a certain number. It's exactly equal to twice
let's go
the Giesecke constant. So this is the simplest 3 manifold there is.
Fundamental argument.
And you
Here we
double
go.
it.
See,
you use the simplest thing that you can. Okay. Well, let's tease apart. Actually, before I go into details, let me run through a fast version of where this is going to take us. I'm saying we have a minimal root here for a structured universe, okay? And that universe, that root here is has a complement. It's like you tied a knot in the wave. The wave has to go around this closed path. But as it's going around, it drags stuff with it and ends up doing all the transformations, okay? It's creating a structure on the outside in response to that, over and over the same structure. That's why it's gold to us, because it's making something that is persistent, right?
It's my interpretation is that's going to set up a field configuration of a particular type that would lead to the stuff and things that we observe in our realm of persistence. That's the ultimate goal. And again, it's a fantastical claim, but if basically this stuff didn't pop up on Wolfram Alpha for trying to solve some of the equations for the constants in nature, if you just look at some of the properties, it's like, oh, that's very interesting. Oh, no, yeah, I think according to the Jones polynomial, somebody proved like a year or 2 ago that the figure 8 knot was basically worthy of Ed Witten's 1989 paper or something. It basically, there was a connection and it was adequate to solve for like an adequate field theory. It was something along it was either from SEMF or maybe one of the Wolfram summer schools. I'm just an LLM, guys. I just go on and just scrape arbitrary bets and just kind of regurgitate them, and we kind of see what works here. Also, the interesting thing is, if you look at this, it's what do we say? We're just talking about roots of -1. What? Oh, look, -1 to the 1/2, -1 to 3. So there's something with a 1/2 and a 1/3. We got 1s, we've got a 2, we've got a 3. Might there be something there that we could gain greater depth and insight in? It's a discussion for later.
Same thing over and over, a perpetual structure. Okay. Well, the outside, to find what it looks like, we just do this. We drop the I, we want the real version instead of the imaginary version. Take the dialogarithm, 1 over the imaginary golden ratio, plus the dialogarithm of the imaginary golden ratio. All I did was change the sign from minus to plus and drop the I, so it becomes the real conjugate of the hyperbolic figure 8 knot. And what is it equal to?
Yes.
It's equal
1, 2,
4 pi
5
squared
3
over 2, 88. It's actually something that brings us directly to Kepler. And
okay, just to rewind, this is a crazy thing. This is something. Okay. Basically, you go to Wolfram Alpha, you type those magical symbols and stuff in, you'll get the volume of the hyperbolic figure eight knot. Okay, you get your I in there, blah blah blah. Okay, what's the difference?
Conjugate
We take
of the
we take the
hyperbolic
I
figure eight
out,
knot.
so this is
And
essentially
what is
the
it
real
equal to?
conjugate. We'll let
It's equal to 4 pi squared over 288. It's actually something that brings us directly to Kepler and the most beautiful limits in hyperbolic spaces and sphere packings, but we're not going to do all those details right now. I'm just pointing out that it has this projection. This guy makes this, so these two come together. Now, this is a double covered sphere. It's a sphere that you make, a unit sphere.
if you think of 4 pi as a sphere, it's squared, so you got a sphere times a sphere. That kind of sounds like a double sphere, or at least that's a particular interpretation. The 288 is a fantastical thing. I'll give the deep lore and the backstory on that, or at least from mine and Thad's perspective, because it was hilarious.
Whose boundary is made twice.
So it's like a double layer, almost.
Double layered sphere. Good.
Yeah.
Okay. And that
Tasty
double layered
spheres.
sphere is divided up by 288 ways exactly. Now, this is exciting because 288 is exactly the number of transformations that the tetrahedron that we're talking about, structure that this is based on, can undergo and still look the same. So this hyperbolic figure eight knot has this many possible ways of being twisted
There's like
into
8
something
different
else.
categories of tetrahedron.
Okay, and
Wolfram Alpha,
288
that's the
happens to be the
generalized
exact
version.
number of constants in nature. Okay, now what's the picture? We've formed the hyperbolic figure eight knot. We've twisted up some domain. Out of this infinite void, we took some finite spot and twisted up some domain into the hyperbolic figure eight knot. Now we have this repeated structure, and its complement, the thing that it makes when we do that, is this. Some sphere that's got a double shell in there, but they're the same radius. Okay.
So this is essentially a container for the chaos.
Yes. Yes. Good. Container for the chaos.
Okay.
Once it's created, the container continues containing itself.
Mhm.
No matter what chaos is passing
Chaos
through it, the
container.
container continues to contain itself in that structure.
That equals Pandora's box. All right. So let's go back for just a moment.
These two come together.
Okay. So we got this thingy. So this is basically a little calculation. You throw that in. That's I. That's the whole square root of -1 thingy here. We get our brackets here. That lie thing right there to the 2. That's a dilogarithm. So it's technically a polylog. What is it? It's taking some form of a logarithmic basis of this particular thing. God, I need to learn more about logs. This is basically the imaginary golden ratio is just 1 over 1/3. -1. That's 1/3. For our exponent there, we're subtracting that. All right. So this I, the imaginary part. Ooh, the figure eight knot is imaginary. That's actually kind of cool. It actually outputs a real volume. But if we get the I out, and instead of a minus, we put a plus, we got 4 pi squared. So we got like 2 spheres divided by 288, as Rick pointed out. That is 144 times 2. I remember when Thad told me he went through and he was looking for like dimensional constants, and we were kind of going back and forth. It's this is kind of only an Earth only thing, or this here. It's like, and again, maybe some could change, but as far as things with different dimensions and or outputs on codata, there appeared to be 288. That was an interesting thing. So that's why things are currently organized into 8 columns and then 36 units within each of those columns. I don't know. Whenever I hear that, my mind just grasps for things. So I hear Professor Neil Turok say, if we implement 36 zero-dimensional fields, we can make sense of stuff. I'm like, well, that number only really comes up with that, or 18 times 2. That's where my mind goes there. But I'm like, all right. Well, this is the imaginary part. We get the volume of the figure eight knot. We take a real conjugate, a double cover sphere divided by the number of constants in nature, aka also the dividing factor of a generalized tetrahedron. Cool. All right. So he went over all that stuff, and let's. All right. It's if he's looking for God's perspective. Oh, well, we'll see. That's the thing. It's like we might just be bound by like the whole Gödel incompleteness. It's like ultimately, can you prove that within the system itself that the rules are true, or do you need to basically be outside the system to basically a higher level Oracle Turing machine or something like that? That's kind of how I take it. Maybe you could guess, but ultimately, kind of seems almost based on an article of faith. Like you need to postulate something. And if it happens to be a really good thing you postulate, it's probably going to go really far. That's my perspective agreement. Let's see. Let's see. We got shekels. Let's see. E8 lattice higher dimensional quasi crystals when projected on it could mirror the. Okay, no, I got to show something else. I'm sorry. This is actually you're going to want to watch Thad's full video if that's something you're looking at. Hold on, I need to bring it up because this he actually he doesn't quite go into that, but there's a very interesting thing that happens. Where was that? Let's build a universe. Where are we? Cosmic map. God, so many things. Okay, let me just go to the thing. I'll do this. Oh wait. Well, you put the link of the doobly-doo, so I can just click on it. Okay. So it happens. Here we go. All right. This is very pretty. This is one of those crazy things where you're like, there's no way this could be right. Okay. Well, let's start with our 5 dimensions. Okay. Our 5 dimensions of measure.
Or length, measures of charge, temperature, and mass.
Hey, what's going on?
All right,
buddy?
So I'm taking our first sphere of our 12 spheres.
Yeah, we're getting there.
What if it's divided by
commit some major
all
blasphemy
of the factored ways that 5 things can factor? All the ways 5 things can factor. Okay.
We'll get into neutron decay.
Completely divided.
Cosmology. Sorry. Let me go back. This is worth listening to. I'll mute myself.
All of the factored ways that 5 things can factor. All the ways 5 things can factor. Okay. Our 5 dimensions completely divide this thing. And then let's take another one that does instead the derangements of 5 things. This is all the ways you can start with 5 things and change the arrangement of them, change the order of them, with the restriction that everybody has to move. Nobody gets to stay still during a swap. Okay, with that restriction, this goes to this. Okay, still for 5 things, it's a rule for 5 things, but it's a rule that everything deranges. Nobody gets to hold still when you're dancing. All right, and then now I want 4 more kinds of spheres. Let's say
like musical chair.
Yeah. Another kind of 4 more kinds of spheres, and I'm going to divide each of these spheres by, let's say this one's 35 things. I'm going to tell you why later in a second, actually. The next one by 18 things. The next one by 32 things, and the next one by 8 things. Okay, these special numbers.
So that's 6 spheres out of 12.
That's good, yes. So let's fix that. Now I'm going to say we want 1 of those, 2 of those, 3 of those, and 4 of those. Now how many do we have?
3, 6, 10, 12.
Good. 10, we have 12 total spheres. That's our outer 12 spheres we're talking about here. All of them together now, but they're divided up differently in the denominator, right? One of them gets divided by all of the factors of 5 things. The other gets divided by all the derangements of 5 things. And then, which is 44, by the way. So this one's 44, and this one's 120. Okay. Here's the cool thing. In mathematics, this is well known. This all collapses to pi to the 12 to the 12 over 12 factorial. Very famous in mathematics for two reasons, which is why it makes it even more famous, okay? It's the exact volume of the 24-dimensional unit hypersphere with radius 1. Okay? This is the volume of the 24-dimensional hypersphere. It's also equal to the exact density of the Leech lattice. So this is a
Yes. That was like a voice then a kind of afterthought. It's the density of the Leech lattice. And, okay. Is this some numerology? Sure, it's numerology. But I'm going to stand by the claim. Numerology is numerology until it explains more than less. I'm still trying to parse this. The sheer fact that this can be factored into something like this and it actually comes out is an interesting thing. Because, okay, so you get a squared factor there. I can kind of justify it. Okay, 32, we're talking about temperature. That sounds very stochastic and 3 dimensions there. And then you've got like 8, which we're saying is the number of things that like mass can do or be deranged by. And that's to the 4th. So I'm sorry, how do I get that? It's okay. Well, mass exists in space time. It's got a frequency. It's got particular magnitudes. Okay. Here's the interesting thing. That Leech lattice. What is the Leech lattice? Okay. Well, I swear I'll actually get to the dang point of this thing. But the question was asked about E8, and I I believe there may be a connection here. The Leech lattice. Go to our friend Wikipedia again. Let's put verify. I'm gonna do a quick once over. All right. Mathematics, the Leech lattice is an even unimodular lattice of 24-dimensional Euclidean space, which is one of the best models for the kissing number problem. Basically, that whole number of spheres or circles and whatever n dimensions that can touch each other and pack there. Okay, so it's discovered by John Leech. It was also discovered, not published, by Ernst Wimp. Okay, 24, determinant 1, blah, 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 blah. That is a giant number, and that looked a lot like the Planck energy. It doesn't have all the same digits. It deviates a little bit. Again, I only remember a few things, and then it kind of okay. Hold on. Okay. The arrangement of all those unit balls about the other unit ball is so efficient. There's no room to move any of the balls. This configuration, together with its mirror image, is the only 24-dimensional arrangement where 196,560 unit balls simultaneously touch another. Talk about reaching out and touching someone. 24 dimensions may be the way to go. Consent matters. This property is also true in 1, 2, and 8 dimensions with 2, 6, and 240 unit balls, respectively based upon the integer lattice, hexagonal tiling, and E8 lattice, respectively. I'm not Garrett Lisi. I was asked about E8. That's the best I can kind of get right there. And then we can see this is where Thad kind of got that pi to the 12th, 12 divided by 12 factorial. Man, 12 really sure is useful. And then basically start getting into different roots of the reflection group of 26. Wait, 26 dimensions? Isn't that the string theory dimension? I don't know. I'm not a string theorist. So, okay. So now that we've gone over half the show, we can actually get to the whole dang point. Let's see, where are we? Okay. People were asking stuff and things. Let's see. Hold on. I'm sorry, I'm a terrible host. Oh yeah. No, I'll go on. Just send me an email or whatnot, man. I said I was going to let that finish what he was saying. That's you are right about one thing, Jack. I need to spend a lot more time doing work. God, I could be so more efficient. Okay. It's charge. Kali, that is a great question. Charge, you want to know what charge is? Charge is time current. It is. It's time times current equals charge. So as you're going to do charge squares, it's time current squared. And I named one of these episodes because it sounded really cool. And it's one of those things that's like, I was a first year physics student. I would have actually known that. you don't do an actual spring equation thingy until like last year. It's like, ugh, wide gaps in knowledge. But there are some legitimate hits, and there is some there, like having a game genie. It's like you don't have to be good. You just you know how to get the magical flute in Mario and warp ahead. That's my best take. Imperfect analogy. Um, again, I think electricity will explain a lot. Uh, well, that's the thing. Numerology. It's you hear folks say, "Oh, this is a bad thing. This is a bad thing." Okay, so and again, maybe this is historically inaccurate, but when you start listening to certain things, according to some accounts, when Max Planck was trying to figure out like the whole ultraviolet catastrophe, he's like, "What the heck do I do?" And it's like out of out of sheer desperation, it's like, "How can I make this work? Let's play around. This combination of stuff and things seems to match the data. What the heck is this? Oh, this is a unit of action, technically. That can't possibly work." And seemed to have worked at least long enough that they named a bunch of units and stuff after them. So take that for what it's worth. Uh, oh, that whole thing. So the interesting thing is Thad's one of the magical numbers within his within the minimal arena or the HF8 model is 5 dimensions of measure. So we can use those 5 ingredients to put them together in different combinations to get the other dimensions that will actually measure. So you can break it into those 5 uh, platonic dimensions, let's say. I don't know. That sounds kind of cool. But basically, if you're going to have a circle, how many circles can you put in that? All right, you can put 7. You can put 6 around the ring, 1 in the center. So now you've got 7. So that's the claim break and scale symmetry. Sounds pretty Euclidean to me. We're breaking up a circle into other circles. Okay. 7's supposed to be a magic number, and a lot of people like 7. So hey, power to the people, I guess. Now if you're gonna do that same thing, how if you have a sphere, how many spheres can you put around it that they would all be touching? The answer is 12. So in 2 dimensions, it's 7. In 3 dimensions, it's 12. That's something to know. Yeah, Rick's got it right there. 2 to the 7/12. That's a perfect fifth is 3/2. But for some reason, music seems to work, and people have kind of vibed and been studying this for a long time, and it gets the old noggin a jogging. We'll leave that at done. Okay, so Crypto's commenting. The action is done when the particle interacts with other matter. See, the problem, I actually don't know if you said that before or after I said action, so I'm unsure if we're talking about the dimension of action or saying action as it's doing a thing. Well, this is literally one of the reasons why I break stuff down into like, yeah, I already used the word. Thoughts, words, cut, stuff, things. Because it could also be things doing stuff. So it's if I don't know what it is, you just and also when you listen to some of Professor Feynman's like Los Alamos lectures and stuff like that, he's like, "Yes, it has been a while since I was involved with awkward pause stuff at Los Alamos." So either he was having a brain fart or he was trying to keep stuff that he wasn't supposed to talk about quiet. So personal opinion, I have no idea. Okay, so it's the track. Wow, this is such a good discussion. Oh my God. Um, all right, so Kylie, let's see if we can't break that. Let's make some okay, let me actually go to the dang board. I got this board here. I haven't erased it in a while. All right, so let's take what Thad says. So basically, what Thad said, the lowdown is if you've got like a void, but basically technically empty with things as we know, you just have random waves. Call it the Roolead, call it your configuration space, infinite dimension, Hilbert space, whatever you want. Uh, Again, my basic outlook is math works and logs are useful. Okay, those are my postulates. The generalized claim from Thad. Let me pop this up a little bit. Sorry, I've been changing some stuff and things. All right, so all right. So the generalized claim. Let me it's back a little bit. Sorry. All right. So the generalized claim is if you got technically random waves and stuff, nothing persists. That's the generalized claim. All right. At some point, given, I don't know if that's a concept of time, but it's like you just got random waves. At some point, there's going to be a configuration of the figure eight knot. Basically, you're going to have two Giesking manifolds come together in a particular way to create that compact, minimal three manifold structure, or at least that double cover of the Giesking there. And it's going to have a very particular articulation as these things seem to be rotating, to my knowledge, orthogonal to each other. And at least according to, oh my God, Professor Henry Segerman, the knot itself, it's technically some rotation to the complement. That's going to be important in a few minutes. Okay. So my claim is that once you achieve that minimal persistence, at that point, whatever randomness or waves are happening, at some point, you've created something that persists. Let's just say if you've got something of persistence, I don't know, kind of like when something persists within our minds, maybe that gives it a little bit of gravitas. Gravitas, you say? I don't know. If you have some form of a component, I don't know. Is this where gravity starts kicking in? I don't know. But my thought is once you get that persistence, all those other random waves are going to swirl around, come together in such a mass amount of energetic force that we're going to get an inversion of that toroidal structure into the N hypersphere of maximal volume. Okay. Now we just need to explain how we actually get there. Okay. So, from my conception, if we're going to start, once you get that, you're going to get everything crashing down. Oh, yeah. Shout out to Jennifer Scharf. She was the one that kind of put that mimetic in my mind just because she's like, oh, imagining something like this. And she was a good describer of things and very brilliant. So I'm just going to take that. So I'm like, all right, that has this knot. If you're going to say there's a randomness of all these waves, it's like, I don't know. To me, and again, listen, whatever you want to study or preferred model you have, that's totally fine. I'm just providing a particular perspective based on what a lot of smart folks have told me. Then again, I am just a dude on the internet. So take it with an ocean full of salt. But if you did have a minimal persistent structure, all that wave energy, so to speak, it's coming in, it's going to come down, it's going to invert. And coincidentally, if you do some calculations, I'm not going to start with the Planck length because listen, if we start off by hand waving, say cosmic fluctuations, and then we get all the matter and the stuff and things in the universe, we got some inflaton fields, we got all this stuff going on here. Okay, I'm trying to minimize that. How do we minimize this? Okay, so I'm going to start at the point, not at 10 to the minus 105 meters or whatever it is, the Planck length cubed, because there's some calculations we can do. So if we have, I'm going to make some assumptions here, and we'll run through the assumptions and I'll provide my evidence for them. And you can all decide if this is something worth putting any energy into. Okay, so we're going to make a claim that how could we try to do some of these calculations? Well, you're going to need to nail something down. Okay. So Dr. Salvatore Pius, I think I was on with Crypto and a few other folks. I think Dr. Pius was on before. But here's one way. You can do, let's do F sub P, so the Planck force This is in Dr. Pius's little paper here. Now, a lot of folks are like, oh, it's the Dirac large number hypothesis. It kind of is, but the way he phrased it, I'm like, at one point he said, well, if we could know one of these things, then we should be able to calculate these other things. I'm like, well, Thad made some claims. Let me explore it. What if, because one of the things I learned from Thad is when he was coming up with the hyperbolic partition equation to try to calculate the amplitude of the fine structure constant, that's that whole Joe one, that silly little x with the one after it. When you square that, you get the fine structure constant, do basically all the known digits. So it's some experiments have pretty good disagreement around the 10th digit or so, but he looked at it. It's like, all right, it gets it for like 6 digit, gets it more than like Euler's constant. It's like, what if it was true? Let us entertain the idea, because that's supposed to be science. You're supposed to try things, you see how they work. Does it agree with experiments? Does it make sense? So he did a calculation. He's like, what lambda would I need to subtract out here for this to be true? To be of the magnitude, and starting to get the first few digits of the Planck mass. It's like, let's plug this in. It seems to work. Imagine that. Maybe there's a connection between mass and charge. Who would have thunk it? So that's all I'm doing. Thad just said, oh, and there's also, I'll do a separate talk on this. It's basically, I think it's the extendability of space-time. Basically, you can, and there are people that have done this, where basically, if you're going to claim there's a minimum, then by argument, that basically, if there's a minimum, there would need to be a maximum. And I think this might be, and again, I'm not a quantum mechanic or a cosmologist or something. That's I'll talk to Professor Kaku or Professor Keating, someone like that. But if we can't get past the Planck length, and we try to keep going because we assume we can go infinitely down, isn't that going to lead to us saying that the maximum must be infinite? Hypothetically, maybe if we stopped at the Planck length, and again, it's not necessarily the math is the territory, you stopped at the Planck length, and that seems to be a minimal unit of length and where we live, what would the maximum be? You just do 1 meter squared over that, because you're going to, one will get you the inverse. If you slap the unit on it, you'll just get it without units. And then if you square the thing, guess what? You're going to get its inverse in the same units. Okay, that's what we do here. So what we do is you do the Planck force, and then basically you take the mass energy of the universe. So we're going to say, oh, no. Excuse me. Because he frames it the other way. He frames it as mass times c squared. Sorry. We want to be accurate to the original works. At least where we got the ideas. Oh, it was also supported because I know Rick did a presentation, and I see Rick doing more or less kind of the same thing. I'm like, all right, so there's some more confidence in here. Maybe I'm missing an 8 pi. But here's the thing. So basically, if we're going to do the claimed M sub u, so massive universe, I know what a grandiose claim, multiply it by c squared, you're going to get the mass energy. And then if you divide this by the radius, we're going to do r sub u, this should be equal to the Planck force. Okay, here's something that we have. We have this by calculation. We have this by measurement, or at least it's two-way speed. Something worth remembering, in my opinion. Okay, how the heck do we get this or this? Because we have measurements for basically about 10 to the 26 meters and like 10 to the, I don't know, 52 kilograms or something like that. Which coincidentally seems to balance out. But what if we did that whole meter squared thing? Let's do that right now. We'll go to our friend Wolfram Alpha for just a moment. Don't worry, I'm not going to critically hit you with too many things. Let's see. Okay, so let's just do this. We go to Embiggen. All right, so okay. So if we do what we were talking about, so we do the inverse. So we got to have this with 2 dimensions, excuse me, this to the 2nd power. So this will be our reference unit divided by our minimum length. And we hit enter. It gives us this really big number. Okay. So all we do with this big number, that's just the inverse of the Planck length in its same dimensions as the Planck length. So we plug that number in there, and then listen, I didn't really understand math after the 6th grade, and then this is like playing video games to me. You just gotta be into it. So let's just take that and literally do like force. If I needed to do all this with an old school TI-83 or anything like that, I can't say. Maybe I would have been into it as much. I don't know. This makes it so much easier. Again, for more detailed calculations, you want to use more numbers, and there are rounding and stuff in here. But for a first level approximation, I think this is a very useful tool. So let's do, okay, so what we're going to do is we're going to solve for x, and that's going to be in kilograms. So x kg, and then c squared, and then we divide that, and hopefully I got this right, and it's not squared on the bottom. Is it squared on the bottom? Nope, okay. And we get this ginormous number. Let's add this ginormous number. So we're solving for kilograms. Let's add kg onto it. We can figure out what that is. Okay. I'm gonna click on this. I'm gonna go back to kilograms. People can argue about the units, but this is how I have it grokked in my head. All right. So we get this huge number. What's that? Like 8 times 10 to the 61 kilograms. It's about 8 orders of magnitude. The ordinary mass, mass of ordinary matter in the universe. Okay, so it's like 10 to the 53 from what we see. Okay. So we get that number there. Okay. So now we have a potential claim for ways we can claim the mass of the universe. The easier way to see this is if we just do this. So we just solve for x again in kilograms. It's divided by the Planck mass. That's what happens when you go down some Wolfram holes. And again, well, I'll just show you. And we're just going to do the same thing, except this time we're going to want dimensionless because we want a dimensionless ratio. So we're going to do meters over Planck length, except we're going to square this bit. And oh, look, that seems to be, the ratio between Planck length over meters squared, because if we invert that, it'd be like times 10 to the 70. So it's Planck here. Oh, look, this looks very suspiciously like the same number. And again, there's some rounding errors and stuff there because it only goes for like about 5 digits there. But what is that? 83 Novan decillion? Yeah, that's a really big number, folks. All right, let's go back to kilograms. Cool. All right, back in kilograms. All right, so that's another way to say it. So we've got that. Now, one might ask, oh, that's just a random number. You just got a random number. Okay, who cares about this or that? Okay, so let's do this. It's actually 8.315. We're going to do that for our calculation sakes. 15. Okay. We've got this number here. Why might this be interesting? So let's do an interesting thing. Let's divide it by something. So we've got a mass. What's something with a unit of mass that we can maybe cancel out and maybe gain some intuition? If I'm playing with Planck things, how about the Planck density? What is the Planck density? Planck density, I just typed the word there. It's this here. It's C5 over G squared over H bar, yes. 5 times 10 to the 96 kilograms divided by meters cubed. That's a mass density. All right. So hypothetically, And if we took our really big number, kilograms, we'll throw our protected brackets because better have them and not need them than need them and not have them, divide by the Planck density. So those of us that have been playing around for a while might recognize some of these digits. At 1.616 times 10 to the minus 35 cubic meters. That sounds very interesting. The digits of the Planck length in cubic meters. So that means if we, we can just use this. So we'll take this. What happens if we multiply by meters squared? Or you could say there's a 1 meter squared. Oh, wait. Sorry. Division. Derp. Oh, look, we get the Planck length. Okay, that's a coincidence. We need some more stuff there. Hey, nerdy, what's going on? Wait, listen, just because if we plug in that mass number, the radius is going to come out to be the same of a black hole of that mass. It does not necessarily mean that we are living in a black hole. It would explain a lot potentially. Can't say that. I can't say. Listen, I see something in the sky. I don't know what it is. Maybe it's aliens. But to say, I don't know, therefore aliens, I cannot make that claim. I'm willing to conjecture about that, but we will see. Being the minimal event horizon. There are very interesting things, and I think I'd love to see more of exploration from other folks that are established, kind of. But you know what? People are busy; they're doing their own things. Okay, well let's go back. Okay, let's do something. Planck density isn't really that well known. Let's do something different. Let's do the rather than that. Let's do how about the Planck pressure? Under pressure. Okay. Oh God, we got speed of light to the seventh divided by big G squared over H bar. Okay. 10 to the 113 pascals. That's ginormous. That's what is that? Planck pressure. Oh yeah. Oh, is this where some people say, I'm not aware of the whole story, that if you were going to assume that the Planck pressure should be a thorough thing throughout, I think this is where some folks say the worst calculation in physics came from, where it was off by potentially 122 orders of magnitude. If you're doing it in Planck length, otherwise it's like 52 orders of magnitude off, because essentially the universe vacuum energy density is a lot smaller than that. Why might that be? That's not for this discussion. Okay, ginormous number. So what is that? It's pressure. So what it is actually energy density. What that means is we need to take energy, which is mass over c squared. So we normally have mass, length with a +2, and then time with a -2. So we're dividing by volume. So that's going to take length from the second power, the length to the -1, because it's a 3 difference. Okay. Well, let's take the Planck pressure. Under pressure. I'm sorry. Dr. Hassenfeller's meme got me. All right. So that's energy. Let's do this. So we're going to take our mass, or at least mass bank might be a better term, because we're supposed to be able to do this little conversion thingy. We get this number here. We multiply by c squared. We get 10 to the 78 joules. 10 to the 85 ergs. Ooh. Difference of 7 there. Interesting. Okay, so we've got that. Now, divided by the Planck pressure. What do we get? Oh, looky. It was that same number we got, because Well, the difference between the Planck density and the Planck pressure is literally c squared. Okay, that was just to lay out the case. I mean, the dimensions add up and everything. Okay. So the interesting thing, why this is also fascinating, is because when you look at this number here, 7.488 times 10 to the 78, and then we've got in joules, so it's energy. Okay. Are there any other numbers using these, let's say, Platonic dimensions configuration that will get something like that? Well, my friends, let's grab our friend over here, and let's go to, hypothetically, let's just say Planck mass over Planck time squared. Okay. Why does this even matter? All I know is I'll see numbers and I won't know what those numbers are. Some of them I kind of like. I'm pretty good at recognizing the first couple of digits and around the magnitude. So if I see these things, it's just kind of like an LLM crawling. Oh, match this. Just see the relationship. I saw this number and I didn't know why this was the number. Apparently, this is interpretation spring constant. Since I never did all that standard physics stuff like that, I don't know all these things, but you could view this as a force gradient, linear force density, surface tension, field strength, or perhaps cleavage. I'm going to take spring constant. Why? Well, if you look at the spring constant, wait a second. 7.488 times 10 to the 78. 7.488 times 10 to the 78. Wait a second. This is in energy because it's got a mass thing here, and this is just c squared. Got a mass here, but there's no length. It's only seconds squared. That's interesting. Why? Well, because it's a spring constant. And it's got the different. We're not going to go through all that. I know I'm over an hour right now, but we're just going to take this. Let's divide them. Let's see what the relationship is. Okay. Oh, look. A reference unit of 1 meter squared. I mean it, and again, do I know all of what this means? No, but it seems to be an interesting relationship that for certain giant numbers like the Planck density, the Planck pressure, the Planck spring constant, technically you could call it that because well, that's the dimensions that happen to come out and it's utilizing Planck units. If it provides an explanation, okay, I'm gonna real quick go through that whole. Let's I realized I didn't even really get to anything that I really. Okay. Ultimately, this is where I can get to where we can start to play out things that might be going on. Because this is the volume, this is basically the Planck length times 1 meter squared. Oh, that little thing that we had there. Because we can just do that. Okay, so we got that. Now, hypothetically, if this is that much stuff and it's that, what does it come out to be? Basically, every Planck volume is going to have a Planck mass worth of mass, or basically a Planck energy worth of energy, or Planck temperature worth of temperature. Because if you introduce c squared and Boltzmann's constant, you can kind of do the translation between the different things. Okay, so that seems like the maximum energy state. We would be at approximately this volume. So about how big is that? So that's volume cubed. So let's raise it to the 1/3 and we do our math. We take the cube root. Let's find a length. What is the minimum radius of this primeval atom, so to speak? Oh, looks a little bigger than the electron's Compton wavelength. So right about the size of an atom. And then once you get there, then you can listen. I don't know all that cosmology and stuff. I don't know if we need expansion or not. I mean, maybe that explains things. I mean, if you're gonna go to this, basically, if where do we need to go to? We need to go all the way back. So basically, if you're gonna start, how long would it take to? We need to go to a radius. Here we go. Okay, we'll go to a radius. So if we got that, I think we got to divide this by c to see how long. Okay, so basically, if we assume, sorry, let me go back. If we assume their radius was the inverse of the Planck length, you got like 10 to the 34 meters. It's about 7 or 8. That's diameter. So if you did in radius, it's about 8 orders of magnitude larger than the radius of the observable universe, which is like 10 to the 26. So the 8 orders of magnitude thing I can parse because, well, if it's 8 orders of magnitude larger, it's 100 million times larger. That's absolutely freaking ginormous. But 100 million, we can kind of get our head around that. Now you're just going to multiply by an already ginormous number. Okay. So if we take this, get that many meters, and we divide it by c, what do we get? We get this. 10 to the 26 seconds. My mind doesn't work that way. How long? Oh, about 10 to the 18 years. Now, current estimates generally accepted, it's a little under 14 billion years old. Okay. 14 billion is a really large number because a billion, we've got 9 zeros. You got a 10 in there. That's already 10 to the 10. What does that mean? Oh, look, about 8 orders of magnitude older than the age of the universe. Now, the difficult thing here is that's for it to hit that radius. The question is, have we hit that radius? And if we have, if we're going to claim some cycles, which I know I haven't got to, I'm a terrible host. But I think laying out this case is important because following through the logic and just presenting the case, because you guys are the jury and everything, and the other folks out there, it's listen, you can figure out everything in the world. Maybe you have figured out literally the answer to life, the universe, and everything, and it's something like 42. Okay. Now, if you have that, you still need to be able to communicate it because there are some folks that are absolutely brilliant thinking, like absolutely way smarter than me. And it's like they're not always the best at communicating things because some people are really good at writing things. Some people are very good at verbalizing things. Some folks are good at kind of like just kind of talking about the topic and they can really inspire you about different things. Not everybody's good at everything. That's okay. That's why we got each other. We can build upon other stuff and things that's going on. Okay. So I apologize. I've been ignoring everybody. Okay, let's just go quickly through. Hey, Geishel. Good to see you. Kali, there was, hey, peace out, crypto. Kali, there's a crazy calculation that kind of goes along with that, where I'm like, if we assume general neutron decay cosmology, I got a random 2 pi that I have no idea what's going on there. We're going to look into it just because it does make a lot of sense. You're right, Jack. I didn't even get to the spin. All right, we'll get that another time. But that's all we got for right now. I got some links and stuff in the doobly-doo. Feel free to check them out. But other than that, hey, take care of yourselves, everyone. Crazy world out there, but I think there's going to be some real interesting stuff coming down the pipeline. So peace out, everybody.